In the event that you have a substitution problem in which you are also trying to do a definite integral, there is a way to handle this as well. Now, for the general substitution problem, we had it set up in the following fashion. And then, for a definite integral, we would say limits would go from x equals a to x equals b. So the typical things that we would do is we would say let u be equal to whatever that inside function is. And then differentiating, we would get the differential substitution that du is equal to g prime of x dx. However, these are not the only x's that are present within the problem, because technically these two values up here would be x values as well. Now, if you are going to make substitutions to turn this into a new kind of integral, we would still see f of u times du, but then it would be necessary to substitute our limits of integration as well. And by that, I mean actually take this value of x and plug it into the substitution, and take this value of x and plug it into the substitution as well. Because we don't know exactly what the substitution was, the notation that we'll use for it is g of a and g of b, to symbolize we took those numbers and plugged it into this substitution. Then we would proceed as normal. So with that in mind, I'd like to consider a couple of cases. For example, let's consider the definite integral from 0 to 1 of the cube root of 1 plus 7x dx. Now we recognize this as a substitution problem due to the fact that we have a function inside of another function. So in this case, we'll say let u be equal to that function that's inside the other function. Therefore, du would be equal to, for the differential substitution, that would be 7 times dx. Now, we don't have a spare 7 in here, so we can use algebra to solve for dx and say that that means that dx would be equal to 1/7 du. Additionally, we'll need to perform a substitution on our two limits of integration. So we can point out that when x is equal to the lower bound of x, we can plug x equals 1 into this expression and get u. Therefore, getting that the lower bound will be u equals 1. For the upper bound, when x is equal to 1, u would be equal to 1 plus 7 times 1. Simplifying as much as possible, we would get an upper bound of 8. So performing all of these substitutions, lower bound was x equals 0, and that corresponds to u equals 1. The upper bound was x equals 1, which corresponds to u equals 8. Based on our substitution, this will now be the cube root of u, and dx will be substituted as 1/7 times du. 1/7 is a constant multiple and can be pulled outside of the integral without penalty. In anticipation of the rule that we're about to use, I'm going to change the cube root of u to be u to the 1/3 power. With that in mind, the constant multiple stays as a constant multiple, and we antidifferentiate u to the 1/3 power. That would give us, in this case, u to the 4/3 power, and divide by the new power. It is not necessary to use a plus c because we're dealing with a definite integral. This is going from lower bound 1 to upper bound 8. Multiplying our two constants together, this will be equal to 3/28 times, plugging in 8 for our upper bound, this will be 8 to the 4/3 power, minus our lower bound, 1 to the 4/3 power. The 4/3 power means take a cube root and then raise that quantity to the 4th power. Cube root of 8 is 2, 2 to the 4th power is 16, and 1 raised to basically any power is going to be 1. 16 minus 1 is 15, 15 times 3/28 will be 45/28. That represents the area that's contained underneath this curve between x equals 0 and x equals 1. Let's try another. For the next example, I'd like to do the definite integral from 0 to pi over 2 of the cosine of x times the sine of x dx. Two things indicate that we should be using substitution in this case. First off, we have the sine of x, indicating that this sine of x is an inside function. I also see the presence of the derivative of this inside function in the form of cosine of x. So I'm going to let u be equal to that inside function, sine of x. For the differential substitution, that means that du is going to be equal to the derivative of the sine of x, that'll be the cosine of x dx. Now that means I can take this cosine of x and this dx and put them together as one substitution. Now for the bounds, we start with the lower bound of x equals 0, and we'll plug that into the substitution. U will be equal to the sine of 0, which is equal to 0. For the upper bound, when x is equal to pi over 2, u is going to be equal to the sine of pi over 2, which is equal to 1. So when I perform all of these substitutions, this is going to be equal to lower bound of x equals 0 corresponds to u equals 0. That's not that uncommon. And the upper bound of x equals pi over 2 corresponds to u equals 1. The sine of x will become the sine of u, and the cosine of x dx will become du. Everything seems very well organized here. Next, we actually anti-differentiate the sine of u, which will be the negative cosine of u, and then we can plug in our bounds. This will be the negative cosine of 1 minus the negative cosine of 0. Now, minus a negative, that's going to be plus, and cosine of 0 is 1. Minus the cosine of 1, I don't know what the cosine of 1 radian is, so I'm just going to leave this in its exact form for my final answer.